with, well, we need to have a little conversation here as a group. So I've been working on grading the most recent tests. And it's seeming like more and more often I'm seeing a disconnect between the work that I see in the homework and the homework quizzes and what we're able to kind of reproduce in a test setting. And it seems pretty obvious that, like somebody's got a student solution manual, or we're using AI, or there's some other resources going on, because the work and the homework is quite flawless. And then we get to the test and it's something different. Now, it's not wrong to be using those things. Like, those are there as aids that can be productive. But the how we're using it seems to be kind of the issue. So you try and you want to check. Perfectly reasonable, right? Normal thing to do. Go back and look through. Did I get the right answer? Oh no, why not? Let me sort through. Ooh, that was it. Okay. Move on to the next one. That makes sense. That's a reasonable way to apply those tools. I've started this and I don't feel good about what I'm doing, and this doesn't seem like the right thing, because it feels like I'm going off in a direction that seems far too difficult than what I should be doing here. Maybe let me go see and check to see if, like, am I chasing my tail here a little bit and not waste a whole bunch of time doing that. Again, reasonable use. What's going to get us in trouble is when we read it and been like, oh, I'm not really sure what to do. Let me just Google it right from the start, without even really putting pen to paper and spending any time like struggling through on things. Because that's where you're going to learn to discard your bad ideas. And if we don't even like get a chance to put the bad idea to pencil or to paper before going and seeing that it's not the right route, we end up still with those same ideas come test time. So it's fine to be checking your work. Definitely check your work, right? Like, do some work, see if it's right. If it's not, go back and figure out what went wrong. Totally makes sense. Even if it's one problem to like kind of get the feel of how I need to start this, like what's the pattern, totally reasonable. But if it's like, I just need to get this set done because I'm overwhelmed and I'm stressed, and like, I just need to get something off my plate, and I can get this off my plate right now by kind of going through this, you're kind of going to bite yourself in taking that route. And if it's a situation where there's too much, we can have a conversation. I'd rather have you do it and do it well and be productive doing it and do less than, like shortcut our way through. And so it looks like we've done it all, but really I haven't done much other than like, well, I've read through the answers and like the answers made sense. But there's a difference between like reading it and understanding it and then being able to do it again yourself without any help, right? So from where I'm sitting, it looks like there's kind of a lot of this going on, and maybe we're getting into too much of a habit of doing that. I need to say something kind of before things go on. I'm not finished grading things yet, but from what I'm seeing as I'm going, like that starting to become pretty clear that this is becoming too much of a habit rather than an occasional, like, I need to help figuring this out, to I just need help getting this done tool. So if we can try to be a little bit more conscientious about how we're using those tools, I think that would benefit everybody going forward. That being said, I have a couple of takeaways from the test on things that I'm seeing that are mistakes that kind of I'd like to address now and kind of get out of the way as things that are not okay to do. So say you have the integral of the product of two functions. Never, ever, ever is that become the product of two integrals. I saw a lot of this. If you have, same thing goes with a quotient. If we have a quotient of two integrals, or a quotient, an integral of a quotient, it is never ever the quotient of two integrals. I saw lots of these two things when people trying to like do antiderivatives. And then the fundamental theorem of calculus says that it's the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. I saw lots of people not doing any antiderivatives at all and just plugging a and b back into the function that you're supposed to be integrating, where no integration happened. All we did is we substituted back in. So again, like, flawless on homework and making those kinds of mistakes are things that like tell me that we're not, like, you're not spending the time kind of working through the homework as it might appear. Hi, come on in. Thank you. Joey, it's for you. And I think it's for 4 minutes ago.
Oh, okay.
So get in your time machine and you better hustle.
Yeah.
It's an oddly specific time as well.
That is.
So again, like, no judgments on this, but like, we have to, like, to do better, and it's okay to struggle through things. It's okay to come back the next day and talk about what's happening, and what we're having a hard time with. I give you the long deadline for the homework so that you can do that, so that you're allowed to start and go, okay. See you, Joey. To come back and we can talk some more, right? Like, it's not most of these lessons are not designed to be a one-day conversation, right? They're designed to, like, okay, I think I understand it. Go home and try it and be like, I don't understand it, and come back and we can talk the next day and work through some more example and kind of brush up on the finer points. And then you can go back and take another swing through and be like, okay, now I feel like I have it, and make more progress. And like, that's the normal for an advanced math class, is it's usually, most of us are not going to be a one-day conversation lessons. They're just not. And they're not supposed to be. They don't need to be. They shouldn't be. You're doing fine if they're not. Okay? In addition to that, I put together this slide just as a integration summary. I put this up the other day, so some of us might have seen it, some of us might not have. So again, if you're doing a definite integral, depending on how it's being presented, the techniques you might use to evaluate something like this. If you have an equation, you can use the fundamental theorem of calculus part 2. You do the antiderivative, and then you plug in b and a to the antiderivative and look at the difference. That'll get you an exact answer. If you want an approximate answer, a rounded answer, your calculator can do that, right? If you have a absolute value involved, remember, you have to chunk that. You have to find out where the function becomes positive and negative, and then break your integral up into the pieces that are positive piece, negative piece, and whether you stick a negative sign in front of the negative piece or you just find the answer and then make it positive it yourself, however you go about doing that, but it has to be chunked into those pieces. Without doing that, the positive and negatives are going to aggregate and you're going to lose what you need there. Do you guys remember what I mean by chunk? We've talked about that, where oh, look, this part is under and this part it's over, so the part that's under I integrate separately, the part that I have over integrate separately. Yeah. If your f of x is a graph and that curve makes geometric shapes like rectangles and triangles and circles and stuff, you can use your geometry formulas and just look at the area under the curve, chunk by chunk by chunk, and you can break it up in as many little sub pieces as you need to. And that can give you an exact answer, right? If you're using geometry formulas to do areas under the curve. If you have something that's not a geometric shape, you can still approximate it with a Riemann sum, right? Or if it's laid in a grid, you could count boxes and approximate boxes, right? That's still valid depending on like what's available to you in the problem. That might be what you'd have to do. And if you're given selected values of your function just in a tabular form, like in a table, probably best you can do is a Riemann approximation, right? Where you can't even make them like equal with rectangles. You can just make whatever widths you have the information to make them, and there you go. But in general, those are the three different presentations you can have for one of these integral problems. Your function given to you as an equation, as a graph, or as a table. And what you can do with each of those is kind of described here. Does that feel okay, Chanel?
First, thank you for making this, because it like makes everything a lot clearer.
Yeah.
Because it's like, instead of going through all the lessons, it's like right here. And then also, is it just for like A to B, or is this also like infinite? Like
If it's an indefinite, which is different than infinites.
Sorry.
That's okay. If it's an indefinite integral, getting a graph, if you have a graph and you want an indefinite integral of that, that's a different, you'd be getting a graph back, and that's much more difficult to sketch.
Okay.
Like that requires some real intuition. Oftentimes I have to really sit down and think and like come up with some points and think about what's going on. So I don't want to say so much about the indefinite version of that.
So for indefinite, what would we have to worry about for indefinite?
More often than not, you'd be going equation.
Okay.
Like an indefinite integral is like your result is another function in terms of usually x.
Okay.
So that's really, more often than not, that's what you're getting. Occasionally they might ask you to sketch a graph. In general, what I would be doing is like, like trying to compute, like eyeball a little bit the areas, what's going on. But more often than not, they'd like, describe the graph as like, like this or something. They'd give you that type of thing and ask you to draw the graph for it, given the graph of f of x or something, which is a little bit easier than just like, here's a graph of f of x, sketch, the integral of f of x dx, because there's infinitely many of them because of the plus c. So like, not probable they'll ask you to do that, but that's kind of what's going on. Does that feel okay? And there's nothing you could do with a table for something like that. Nothing you could do.
So would you just like follow those guidelines, like f of x is an equation?
Yeah, more often than not, that's what you would be able to do. I mean, you can still like, if you have an equation, you can make a table from it, and you can make a graph from it. You can still do those things. It's just not, it's like adding an extra layer, right? But probably I would avoid doing that, because if they give you an equation, they probably want you to use the equation more often than not, unless you see like an easy shortcut. And you might not. Okay. I was gone on Thursday, left you guys a video. Did we watch the video for the lesson? Was it hard?
Yeah.
Okay, let's kind of go through the main idea here, and then we'll do some more example here from the homework together. Yes, Pierce?
Can I go to that?
Certainly. Great.
After this, can we retouch on 6.1?
Sure, yeah. So in 6.2, the idea was we're looking for volumes of solids, right? So like, you have, some like kooky looking thing like this. It's not a cylinder, it's not like a pyramid or a rectangle or a rectangular solid like a prism or something. It's not something that we have an easy geometric formula for, right? The idea was that, okay, well, if I take a little tiny thin slice out of this thing, what I end up with is, in this case, something that's basically a little tiny cylinder, right? And if the height of that cylinder is like this delta x slice, so if I wanted to calculate, I could do the volume of that cylinder. And if I take infinitely many, or if I take it and I slice the thing up, I got a bunch of cylinders. I can calculate the volume for each of those cylinders, because now the base and the height, or the two bases, are basically the same, right? I can slice it thin enough so that the two bases are approximately the same. If I slice it infinitely thin, they are exactly the same. If I add up infinitely many things, this sounds like a integral, like heading to, Riemann sum heading to an integral, right? So again, remember that our our definition for an integral is the limit as n approaches infinity, the sum, I equals 1 to n, f of x sub I delta x, right? Where this f of x in our case is going to be like the area for the cross section from our figure. The delta x is going to be like the height of our cylinder. And I say cylinder because almost all of these that we're going to see here today are going to be like something is rotating around a line or whatever, and you're going to get like a circular shape. So like our slices will end up being cylinders. But like that's the height of your three-dimensional figure of your slice. So the slice width is like the height of the thing. And we're going to add those up, right? When we do infinitely many of them, it's an integral, and that's kind of the idea. Does that jog our memories here a little bit? So the trick, more or less, is figuring out this cross-sectional area, right? So if that cross-sectional area is a circle, it'd be like pi, and then we'll write r of x squared. So it'll be the expression for the radius, usually in terms of a variable, squared. If it was a triangle, it'd be like expression for the base times expression for the height. If it was a rectangle, it would be like expression for the length times expression for the width. And you guys kind of get the idea, right? So these dimensions in our cross sections are going to be functions of x, or depending on how we're doing the slicing, maybe y. Now, Braden, you made a face when I said maybe y. And the reason that sometimes you'd slice one way versus the other is you want to slice so that the cross sections are all the same figure, geometric figure. So like if I slice this thing vertically, I'm going to get circles the whole way, right? Every cross section, if I slice vertically. If I tried slicing this way, though, I'm going to get all kinds of weirdo looking things, right? That I don't want to do, right? So if this figure was just oriented up and down, then I'd want to slice that way because I'd get circle cross sections the whole way through. Does that make sense?
Yeah.
So in that case, everything is going to be differently described, right? I'll be doing things in terms of y instead of x. So let's go and do some examples. I'm just going to work through some of these homeworks. I'll do a couple where I do most of the talking, then I'll ask for your guys' input on the next one, and next one after that we'll maybe let you guys try and see how far we can get and then go through things. I really encourage you to have something out to write with, be active participants in this, try to be a step ahead, follow with what we're doing. Pencil, paper, OneNote, whatever you want to write with is fine with me. Have your calculator out. We're going to show you like a way that we can check our setups without having to like.
Can I go to IT so I can see this?
Where we can check the setups without actually having to like look up the entire work, right? Which is nice as a way to avoid having to like see the entire problem if I just want to see how I'm doing. Chanel, what's up?
Should I put my calculator, Mr. Blue? Mine is like dying.
Yeah, of course. I got charger down on the power strip too, so plug yours in while you borrow one so you can leave with a fully charged calculator.
Sure. Thank you.
Yeah, anytime. That's what they're there for. So I think I assigned like 1 through 17 and then a couple of others. We're just going to start with number 1. Again, probably some of us have tried these or started some of this. Maybe we haven't. It's been a busy week. I know everybody's feels like they're at their last one or two wits about them, but we're going to start some now. So 1 through 18 says, find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, and a typical disc or washer. So there's going to be 3 sketches that I'm going to make. I don't really need all of them to do the problem, but when you're beginning, it's really, really helpful to do all 3 of these sketches to start with, so you really understand what it is you're looking at. There's some imagination involved here. There's being able to see things in 3 dimensions and move things in 3 dimensions that can be really helpful in terms of building some intuition on how to get these things set up correctly. But make no mistake about it, this is one of the more challenging things we're going to do in second semester. So this is, much like, the related rates or optimization problems in first semester, it's hard because of the setup. The calculus piece is usually pretty easy. It's the setting up that's the trouble. But we'll go through these few here today slowly and carefully and try to get you guys participating alongside of us to get you feeling a bit better about what's going on. All right. So our first curve is y equals 2 minus 1/2 x, and it's bounded by y equals 0, x equals 1, x equals 2, and then we're rotating about the x-axis. So y equals 0, what is that? It's the x-axis, right? Okay, so that's one of our boundaries, is the x-axis. And then we have x equals 1. That's a vertical line through the x-coordinate 1, 0. X equals 2. That's another vertical line. Everybody feel okay with so far? And then my third boundary is the curve y equals 2 minus 1/2 x. So I know that whatever I'm doing is in here, right? Okay. So to graph, what kind of curve is y equals 2 minus 1/2 x? Linear. How many points do I need? 2. What point should I use? What x value should I pick to get the points?
0 and 1.
I would not do that. 1 and 2.
Oh, okay.
Why 1 and 2? Because those are the boundaries of my curve, right? My curve is I only care about it between 1 and 2. Well, give me the start, give me the end, and I'll attach with a straight line, right? So I get plug 1 in, I get 3/2. I plug 2 in, and I get 1. So again, I'm going by half units here. So I have 1.5, and then 1. So I have that. Everybody feel okay? All right. So the area that I have is this like trapezoidal shape here. We feel good on that? Feel good on how I graphed it and figured out what the shape was going to look like? Now we're going to rotate that about the x-axis. So imagine in your mind, we have our little trapezoid, and it's going to spin around the x-axis, right? Now think about the 3-dimensional shape that traced out. Close your eyes and try to imagine this in your head and think about it like coloring as it goes. So it's going to be like a circle on each end, right? And it's going to be like connected like that. It'll look like a cone with the tip cut off, right? Can you kind of see that though?
Yeah.
So again, it's going to take some practice to see what the shape is, but it's really important that we start being able to do this, particularly when there starts becoming like when the figures become concave, meaning there's like an indent in it or something, or even has a hole through the middle. So this can get more challenging as these figures get more complex. So it really helps be able to envision what these cross sections look like if you can kind of see how the thing is mapping in 3 dimensions. I don't have a better way of you doing that than just kind of like imagining and like using some creativity. Again, if you need to like cut a sheet of paper and like think about it spinning, and it's like, okay, this traces a circle here, this traces a smaller circle there, this is straight in between, so it's like you can have like a straight edge or a flat edge anyways, instead of like something curved kind of connecting them. Does you kind of get what I'm saying? I mean, it's all a curved surface, but it's a flat curved surface. Like a sphere is a flat curved surface, as opposed to like, you know, a golf ball that has a bunch of dimples on the outside. Okay. So that's like my figure. So here's like the x-axis running through it, right? So if I make any cross section, am I going to want to cut this vertically or horizontally? Vertically, right? Because every cut is going to be a circle, right, when I chop it. If I go the other way, I'm going to have like a wedge and then like something else and like an ellipse at times. It's going to be yucky, right? We don't want to do that. We want them all the same shape so that our cross section is the same. So everything we're adding up is still like a cylinder. Does that make sense? Okay. So again, if I take that cross section then, oops, it's just a circle. Everybody agree? So again, I sketched the figure or the area that we're rotating. I sketched a 3-dimensional picture and I sketched a cross section. Is everybody okay with that? Now, in practice, when I do these, and as you get better at this, if you do these, the only thing we probably really need is the first picture. But until you get good at seeing what that cross-section looks like, draw all 3. Okay? Draw all 3. It's worth our time to draw all 3 in the beginning. As we get better at visioning these things in 3 dimensions, you can discard doing all of the 3 pictures. But until you get good at that, you should draw all 3. Drawing all 3 will help you get good at it. Okay? So, if I take some cross section here, some x, and I look for the radius of that, that's the same thing as like picking some x here and drawing that. That's the radius of my cross section, right? Did you guys see how I went from the 3-dimensional picture to the 2-dimensional piece? Okay. So notice that point R, or I'm sorry, that segment R starts at the x-axis and ends at the point x comma y on the curve y equals 2 minus 1/2 x, right? Everybody agree? Any point, so, okay, so what is R the same as? As the y coordinate at that point x comma y, right? Now that y coordinate is a y coordinate on the curve y equals 2 minus 1/2 x. So I know every point on that curve is of the form x comma 2 minus 1/2 x. So my r of x is going to be 2 minus 1/2 x. Does everybody feel okay with how I've gotten to here? So, since my cross-sectional area is a circle, my area function should be pi r of x squared. And now that we have our area function, we're ready to write our integral. Chanel.
Wait, why is it pi r of x squared? Is it because like
What shape is our cross section?
circle? Wait, so it's
Pi r
so
squared.
pi r squared,
Mhm.
and then the radius. Oh, okay.
And our radius is a function in terms of x.
Okay.
And that's normal. It's hard in the beginning to see the shapes. As we do this over and over again, you're going to see the patterns. You'll get better at imagining it. And sometimes it's just going to be a little bit hard. It's going to be hard for you. Some of us, this will come very natural to. Some of us, it won't. And that's okay. The good news is these problems, once you've done enough of them, you see that they're all basically the same. And even if your imagination isn't great, it's like, okay, I know because this looks like this in the two-dimensional picture. I know how to set this up. But it helps if we're able to kind of get a little bit better at the imagination piece. Okay? It's still doable even if you have a bad imagination. If you have a good imagination, it just makes it usually a little easier. But it's still eminently doable for every single one of us, regardless of our level of imagination. I promise. Okay. So our volume is the integral pi r of x squared dx. What values am I integrating at or from? Where do I start my slicing? 1. And where do I end my slices? 2. Excellent, right? 1 to 2. All right. How do I integrate this now? Oh yeah, let's do this first. Take out your calculator. Type this in. When I look this answer up in the back of the book, it is 19 pi over 12, which is approximately like, I think it's almost 5. Let me try it real quick. There you go. That's what you should get in your calculator if we've set this up correctly. Now, if I am you, and we're doing this for the first time, I'm going to do, after I set it up, before I actually try to integrate anything by hand, I'm going to type it into my calculator and see if I get the answer in the back of the book, so I know that, okay, my setup is wrong before I start chasing some integration problem that maybe is impossible because I set this up wrong. Let me make sure that I have it set up correctly. And then I can go, if that's wrong, I can go back and look at my setup.
No, 5. And then in parentheses, 2 minus 1 half x. You put another one.
Okay. You got it, guys? The calculator piece? Good. Okay. So, yes. All right. So to integrate this then, what should we do? If we want to do this by hand now. So you can do a u substitution here. Sure. If you wanted to do that, what would we use for u? Okay. Then what do? We do the derivative of that, which is negative 1/2. And then I need to get the dx by itself, right? Right, so I multiply both sides by negative 2 and then multiply both sides by dx. right? Or you can think about like cross multiplying or something if you wanted to.
Yeah.
Just stick the negative with the 2, and you can think about it that way. That's fine. Okay, and then we should do one other thing here. What else should we do? I want to redo the bounds.
Oh, so 1 and 2.
So what is u of 1? Yeah, and what is u of 2? So we'd write this then as the integral from 3 over 2 to 1 of pi u squared times negative 2 du. Is everybody good with translating that into u sub form? Great. So Pierce is dead on. So we're going to have to flip the bounds now. So in doing so, we're going to take out the negative 2 pi out front. And then when we flip the bounds, what happens? It makes it negative again, so that just turns it back to positive. And we have u squared du. Yes.
Why do you flip them? Is it just to get it in like the proper order? Is that why? Like,
yeah, you could leave it the way it is, and the negatives will take care of itself when you do the subtraction. But I usually do the flipping because it's just like one less negative rattling around for me to screw up later on, because you get too many negative signs bouncing around and whoo. Okay, what do we do next? Not yet, because we haven't done an antiderivative. Right? What's the antiderivative of u squared? Good. And now we can sub in, right?
Wait, how did you get? Oh, wait, I'm just. Oh, wait a second. Never.
I'm happy to slow down or to re-explain anything, but you'd have to direct your questions to me and back to where I lost you at. But I'm happy to do some more, re-explain or slow down. Braden.
Can you just slide?
Was that enough?
Can you go back to when you substituted in the?
Emma, did I lose you someplace? You were doing a lot of mumbling.
So when you got the antiderivative, what exactly happened after that? With the 3 squared, like 3 over 2 squared. But like.
So remember. This, right?
Yeah.
This is like my f of b. That's like my f of a. Right? Because I've done is plugged this in, that's my f of b.
Oh, okay.
And then I plugged this in, that's my f of a.
Oh. Okay.
Feel good? Okay. So let's see, what does that give me? That gives me 9 over 8 minus 1/3. Still have the 2 pi out front. Got to make ourselves a common denominator. That's 27 over 24 minus 8 over 24. That's going to give me 19 over 24, and I'm going to multiply the 2 pi through. That gives me 19 pi over 12, which is indeed what we had said we were supposed to get. Alternatively, if you didn't want to do u sub, this problem is still doable without doing a u substitution. Let's go back and look at the original and see what else we could have done. If you didn't think to do a u sub here, still doable without doing that. What would have we done instead? What could you do with that? I wouldn't graph it.
Oh, you can plug in the values.
I wouldn't plug in the value.
Where?
Well, you don't distribute.
Foil. Wait,
You,
no.
yes, you foil.
Yeah.
Yes, you'd foil that out. Yes. So I'll pull the pie out front.
Oh.
Mm-hmm.
How many on the back?
Yes. So we could have done that. And now when you do your antiderivative, you can just go piece by piece by piece. And it's relatively easy also, right? You guys see what I mean? I'm going to ask that again because I got grumbling of response.
Yeah.
When I say you could do that piece by piece by piece, yes, we see what.
Yes.
And now that's an easy antiderivative to do, right?
Yeah.
Okay. All right.
Thank you.
Sure. Okay. Yes, Pierce.
Sorry, I know you said that you could double check, but from there, you would just take the antiderivative, all those things, and just plug in where A would be.
Yeah, so I'd have 4x minus 2x squared over 2 plus 1/4 x cubed over 3 from 1 to 2.
Okay.
Yeah. Okay. Yeah. Again, that was a problem where the U substitution was unnecessary to do. Either way of doing it is fine. The place where the U substitution is nice is when you got to stuff plugged in. This arithmetic turned out to be a little bit easier than the other arithmetic was going to be. But the algebra is maybe a little yuckier to get there. In most cases, if you don't have to do U substitution, you're probably better off not doing U substitution. Unless the power is like, if this was like to the 5th or something, then I would certainly have done the U substitution because, good Lord, I'm not going to spend the time to FOIL out 5 of those things. Or do I remember the binomial expansion formula well enough to feel confident about, I'd have to draw out Pascal's triangle to get the 5th row. Yuck. I'm not doing that. Yeah, you're supposed to. You're supposed to forget about it.
Oh, I did.
Yeah. Emma didn't even see it. Well, because you didn't take you would have only seen an honors algebra 2.
Oh, yeah.
And you didn't take the course, so you didn't see it, right? So, Emma, you have good excuses. The other people just forgot it. You never even saw it. So, there you go.
Well, I don't know. I thought I was supposed to. I was supposed to say it.
If you were an integrator, you certainly should have seen it.
Oh, well, I did drop out. So.
Oh, okay. Well, at some point, I think you probably would have.
First semester sophomore year, I guess.
I would have thought you'd see it by then, but I could be wrong. Yeah, I would have thought you would have seen it freshman year.
Geometry?
Integrated?
Oh, wait, I did take theory. What am I talking about? Okay.
All right.
It was on full, so I dropped it.
Not really.
Nope. Can't remember.
All right. Let's try this one. What do I start by doing? This one I'm going to ask you guys to kind of help fill in some of the steps. I'll still do most of the work, but I'm going to ask more from you guys. Okay? Actually, let's not do this one. This one is almost identical to the previous one. Let's do the next one. I want one that's a little bit different here, so we can do a little bit more. I'm going to do, let's do 5. That's a little different. Or different enough for me.
So, what is going on?
Same directions. Okay, great. So Christian says start by graphing it. What are the bounds?
0. Well, x equals 0.
Okay, x equals 0 is the y-axis. Okay. And y equals 9. I didn't give myself enough space, huh? I'm just going to do this. So that's 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Everybody's okay with me cheating there? Felt easier than rewriting it. Okay. So I have that. And then I need the curve x equals 2 square root y. What seems weird about this?
The square root of y.
Yeah, it's written as x equals rather than y equals, right? Is that going to change how I approach the problem?
Yeah.
Not especially.
But how do you graph? Oh,
I'm just going to, instead of making an xy table,
y.
I'm going to make a yx table. I'm going to choose the y's and use those to find the x's. So what's the smallest y I can choose? 0. Why can't I choose anything smaller than 0? Because I can't square root negatives.
Can you choose like 4?
You could choose 4, absolutely. But I asked for the smallest thing. The next thing Christian says to pick is 1. Why 1? Because the square root of 1 is a real whole number. I like that. So when I plug that in for y, what does x have to be? 1 times 2. 2. Okay, what should be the next y I choose?
4.
Good. What is the x going to be then?
4.
Great. And the last y I'm going to choose is, and the x there should be 6. You're doing so good, Knowles. Everybody feel good about the graph that we've drawn?
I like it.
Not too bad, right? Where should the shaded part be?
The upper part.
Yeah,
Yeah.
good.
Oh, well, yeah.
Because we know that x equals 0 and y equals 9 are part of the boundaries for the figure, right?
Yeah.
So those have to be edges. So there's my shape. Now, which way are we rotating?
Y-axis, so that means
So we're
like
going,
Like a cone kind of.
I'm getting like
upside down,
like
like
a
an ice cream cone.
like I'm getting a
oh, yeah.
punch bowl,
It's an
you
ice
know,
cream cone.
with a rounded bottom.
Wow.
Yeah.
Yeah.
So it kind of looks like half a pill.
Oh, I actually can't see it this time.
Yeah.
It's like a bucket. Like an ice
Oh,
bucket.
maybe.
Yeah, without a flat bottom, though, right? The worst kind of ice bucket where you set it down, it just falls over and spills.
There's two whiskey glasses there, it's like a ball in them, so they tip. My dad has them. They're weird.
I have not seen
Always
those.
laid it inside.
It is weird.
Yeah, because it's better for those.
Yeah, I don't understand.
Okay. So
Yeah, my dad's a good whiskey glass.
there's the y-axis coming through, right? Which way are we going to be slicing?
I would say this way.
Horizontally, yeah.
Then you have circles, right?
Mm-hmm. That's correct.
Okay. Thank you.
Yeah. And in general, if you're rotating about a line, your cross sections are going to be circles.
Ow. Score.
Okay?
This would be solving in terms of X, right?
No. Yeah. So again, we're going to be doing that, right? Or that's the y-axis this time. So our slicing is going to start here at y equals 0, and we're going to continue slicing until we get to the top at y equals 9. So when I integrate, I need to be integrating with respect to y.
Because those are bounds.
So again, think about the slicing. Like that's why I started with like the theory about what this is doing, because it really gives you a lot of intuition about how to set it up.
Oh, because that one's.
Yeah. In general, if you're slicing perpendicular to the x-axis, we integrate with respect to x. If it's perpendicular with respect to the y-axis, we integrate with respect to y. So this one is a dy problem. All right. So this is like some y value then we've chosen. And that's like our radius, right? So that's just some point, x comma y, right? Here the radius is
4.5.
x.
Because that's the.
Well, when I plot this point, this is x over and y up, right?
Oh, okay.
Does that, Talika, you feel good about that?
Yeah, even though it was blue.
You know what though? Like if you didn't see it, you didn't see it,
I
right?
didn't see it.
All right. But I need this to be in terms of y. So what is x on this yellow curve that we've drawn? Yes, good. 2 square root y. Because I know literally x is 2 square root y.
Yes. Yes.
That look okay? Okay, check it on your calculator, see if we get the right answer. This is 5. This one should come out to 162 pi. Well, I have the answer key sitting in front of me. So like 508.9. But check the setup on your calculator.
Wait, how do we do y?
You just use an x.
Oh,
Remember, when we integrate, the variable doesn't matter.
I got 502. I got 502.
I got 5.
I never even. What does that say?
508.9.
Is 502 close enough or not?
I don't know what. You typed it in exactly like it looks?
I think
Yeah.
so. I can wait, I can show you it.
And it's,
Yeah, I feel as if.
you still have dx at the end,
Yeah.
No, it should be D. Oh, yeah, if you
right?
did,
'Cause I did
yeah.
x for the
Yeah.
y. it's
Same.
Yeah, I got 500.
Oh, I wonder if,
No, so you can't have it be.
right, did we set up look just like this?
Yeah.
Wait, what's the answer? 502 or 501?
It's 5.
Huh. Yeah, I guess the approximation is, oh, I'm in degrees.
I'm in three.
Oh, it did the same thing, huh?
Shouldn't matter though, right?
Well, I don't know what, here's the thing, Pierce. I'm not sure what the code
Oh,
looks like to do this approximation because it's not doing calculus. It's probably doing some Riemann thing. So I don't know if the degree or radian matters. Chanel.
Why is it starting at 1 and 9? Why is it starting at 3?
Oh, yeah, why is it? That is a great question, Chanel.
I see.
Why isn't it starting at 0? Should it be starting at 0?
No.
Definitely should be starting at 0.
I got 508.
Oh,
You were so lost.
Chanel, you're so smart.
I
I
didn't.
got
I just.
508.
No, I just thought that
Isn't
like.
that the answer?
508.9?
Yeah, yeah.
Isn't it like ranging from 0
Yeah.
to 0?
You're salty shack.
508.94.
I can't believe I caught that, Mr. Floyd.
Great job.
Thank you.
Yes, buddy. No more AP business or AP calc. No, you're not.
Does everybody feel okay with the setup now? See how nice it was checking that we found a little mistake? I was really surprised that if it was going to be that off. I wouldn't think it would be.
Yeah, it's five or no.
Yeah.
6.
Too many for that to be not a mistake. All right. So let's integrate now. What do you want to do that?
Calculator?
I mean by hand.
Oh,
To integrate this by hand. We just use the calculator to check it.
you substitution.
No.
I wouldn't U sub it.
You FOIL it?
Well, this isn't a FOIL problem because there's nothing being added and subtracted.
Oh, will you square the inside or?
Yeah. Right?
Oh, what?
Just for
Yeah.
Y. That's
2 squared is 4. Y squared is y.
Oh.
So this is just 4 pi integral 0 for 9 y dy.
just Y squared.
Yep. So we do our antiderivative, y squared over 2. So 4 pi times, well, let's write it as 9 squared over 2 minus 0 squared over 2. So 81 times, well, if I multiply the 4 in, the 2's cancel. 81 times 2 is 162. It's okay. So I did the antiderivative, yes. And then we plug it into the antiderivative. The upper minus the lower. All right.
Could you simplify it to just 2 pi, like y, and then just go from there?
Yes.
Plug in 9?
Sure. Yeah. So Christian says right here, could I just do 2 pi y squared, 0 to 9? Absolutely.
That's so smart.
Save yourself a fraction? Sure. Absolutely. Yeah. Good thought. Good thought. All right, let's see. What do we got time-wise? 20 minutes or so? All right, let's see. Let's do 11. I'm just kind of grabbing some of these.
Oh.
Nope, 6-1 is area between two curves.
No, what the heck?
What was there between 6.1 and 6.2? Like,
Area versus volume?
oh, volumes. Got it.
No problem.
Did I confuse why is it now it's confused.
What's up?
But you have to do both of them?
So,
Y equals x squared. Isn't it just a parabola? Isn't it just a parabola?
Yes, so you need 3 points. Like square root of x.
But which one? Really?
No, you do it for both.
So 3 points from both.
Yeah, you do a x, y table and then a y x table, right?
sure, you can think about it that way.
So no.
I like that. What point do you have to have on the parabola?
0.
The vertex,
One.
which in this case is what point?
1.
0.
0, 0, right? Is the vertex.
Yeah.
How do you find the vertex in general for any quadratic?
Isn't that like a formula for it?
Mm-hmm. Is it
Squared over 4
B
Is
over
it-
a squared.
is it one that you should remember?
Yeah. Is it b squared minus 4? No.
No, dude.
B over 2, right? Oh, so
Yeah,
now
B
you-
over.
Oh.
Why? Yeah, you're right.
Does the AP expect you to remember that?
Yeah.
Yup.
I mean, they expect you to know that for the SAT, so.
Same. Why did
Dude, I gave Gavin that.
Oh, whoa, how did you do that?
Is it? Wait.
So there's, oh, great. Oh, oh, it's one side.
Mm-hmm.
Oh, that's cool.
Wait, so it's the same thing.
Nope.
No,
No,
it's not.
One of them is on the y-axis.
Sorry, guys. Hello. Whoa.
Yeah. Hey, I got a wacky shape.
This is cool.
Yeah.
Wait. Oh, wait. No.
Solve that little crossover section.
Around y.
About.
That's our town.
Oh, so you get like a
Oh,
small point here, big point here. There's a hole in the middle, right?
Up and
And there's a little like, right?
I can't. Like, I feel like it'd be like.
I would think it would be like,
It's like a hole pretty much.
yeah, like a cup.
Yeah.
Yeah.
There's a little bit of
You feel
space on the
Like, look at
inside.
it and then go like this. Kind of. And then you see like how it's
It's
top
like
of
a
a bowl.
tiny bowl.
So it's like a bowl.
It's like a dome.
I think it's a bowl. I like an urn.
Yeah, it's one of those handheld cups.
It kind of looks like, it kind of looks
Okay, now I'm confused.
Oh.
So it's going to have like a point at the end because of this right here. I'm sorry, not that right. Because of that right there. That's like the point at the end, right? This is my line, y equals 1 coming through. Because that part stays there, right? Now it's going to be curved on the outside. It's going to have like a balloon shape because this piece, the outer edge, is going to be curved. And the inner edge is also going to have a curve to it. So it's going to be like there's a Hershey kiss missing from the middle of it.
Yeah.
I don't get it.
So it's kind of like a gumdrop that kind of has a point.
Mm-hmm.
And then inside the gumdrop, you've like pulled out like a Hershey kiss.
That's because of the overlap. Is that what it's all? Like, why?
Why there's a hole?
It's just the way it-
So, Talika, the hole is coming because if there's, when we rotate it around, that space there in the light green is all open.
Okay.
That's empty. So there's going to be a hole in the middle of this.
Okay.
I shouldn't say a hole, but there's going to be convex. There's going to be a cave because there's no opening. You can't pass through it. Like it is closed because there's like a tip to it right here. So you kind of see that.
Ish. Are the cross sections circles?
What do you mean by circles?
Like oval? I mean, what?
That's your cross section.
Yeah.
Because if you chop,
What's
it's like a donut.
Sorry, I know. Look, guys, is it Fat Tuesday tomorrow? Oh.
You would know, Nolan.
What's up, Chanel?
Wait, so I don't get it. So the reason why there's a Hershey kiss in the middle is because, like, you have to account for that rounded part. Like,
So see this right here?
yes.
That's open space.
Okay.
When you rotate it around, that space stays open,
Oh.
right? Like that's not part of it's not part of the solid. Like this end is solid all the way, but the further you get away from there, the more there's open. Do you see that?
Yes.
Okay. Okay. Everybody, Braden.
What would the look like if, for it to be like a normal cup where it's curved on the outside and it's not like curved on the inside as well? What would the green part of the graph have to look like for that?
I'm really bad at going reverse from 3-dimensional to 2-dimensional. That's like a topology skill that I just never had to develop.
I'm thinking it would have to be a lot like closer to the red graph, right? Or like follow the shape of the red graph of that.
Maybe?
Like it's like just like
Yeah. Oh, you mean like a, yeah.
a cup shape.
So it'd be like something like this,
Yeah, okay.
I would think. Emma.
What is the donut? What
It's
is that?
the cross.
So again, this is our line like y equals 1 coming through the middle of the donut, right?
We took it, that's not
Oh.
So I have like an inner radius, then like an outer radius.
This one's too complicated. Okay.
Wait, so then
So my area is going to be pi r outer of x squared minus pi r inner of x squared.
can you just plug in 1? Oh,
No, we definitely do not know it's 1. Okay. I wish I've drawn my picture bigger. Okay, let's give everybody a minute.
Did you say outer minus
It's RI. It's outer minus.
Oh,
How-
yeah.
Yeah. Everybody's okay?
Yeah.
Okay. I wish I've drawn my little picture here bigger because now it's going to be a hassle. All right. So, what color did I use down here? I used the light green for R inner. Great. So if I pick, that's like where the center of my figure is coming through, right? Is on the axis of rotation. So I have that distance there is R inner, right? How far is that distance?
Square. 1 minus 5.
That's 1.
Oh, no, the entire one? Oh, so no.
Because that's 0, and the dash line is y equals 1. And then how far is that part?
Oh.
Oh, that would be 1 minus R.
That'd be y, right? Because this point here is just some x comma y, right? So what is Ri going to be? One minus y. But in terms of what variable should we be integrating? X, because our slices are going to be perpendicular to the x-axis, right? We're going to be slicing this way, vertically.
Oh, is this vertical? Is that vertical?
Right? We drew our slices vertically over here. So I need to rewrite that in terms of x. So on the green curve, x is equal to, so if I want to get that y, great, plus or minus square root x, but which one are we on? The plus end, right? Can everybody see why?
Yeah.
Because we're in the part of the parabola above the x-axis.
We have to, whatever intersected, whatever equation where it'll intersect both positive and negative axis.
But if that happens, we have to do something different. That's a tomorrow problem. So that's our Ri of x is 1 minus. I don't know why I went to capital letters here all of a sudden. Yes.
How do you know which equation?
For Ri,
Yeah, to substitute.
because the first line I intersected was the green one, which was what and then I went back to I labeled the function green before when I drew it. Is that okay? Okay. And then my outer would be this one. Again, how far is this? How far is that? Y. So how far is this? And what's y in this case? X squared. And now we're ready to go. So we're going to integrate from 0 to 1. 0, 1. Right, that point up here is 1, 1, where it ends. And we have pi 1 minus x squared squared minus pi 1 minus square root x squared dx. I'll save everybody the time. That's the correct setup. How should we go about integrating this? Yeah, I like that plan. And I can distribute that negative through, right? Is everybody okay with me kind of real timing doing this? Let's do, yeah, everything is, nothing can combine now. Um, 4/3. Guess I don't need anything there. Oops. Doesn't matter. So what do we have? We have negative 2/3 plus 1/5 plus 4/3 minus 1/2, right? Common denominator would be 30, I think. So that's 26 minus 15 is 9. That reduces down to 3 pi over 10. Nope. I did something wrong when I did my comment, or I did my addition, or my arithmetics there. So this was all right to there. And what did I do?
Oh, it should be. It should be 11. 11 over.
Okay. Thank you. I don't know. I did something dumb. It's like I did all the did the hard parts, right? It's like adding integers apparently got me there. Okay. These are tricky, right? Take some practice. Go slow. Draw some pictures. Think about it. The hardest part is like this. Draw a big picture, bigger than what I drew. Give yourself space to draw. Think about what the lengths of things are. You guys are doing good. Okay? Just go slow and be careful. Don't shortcut through these. These are ones you definitely need the practice. You need to ride the struggle bus a little bit. The aha moments will stick if you let them become natural aha moments, right? If you try to just like Band-Aid your way through this, nothing's going to stick, and you're going to get to the test and be like, I mean, I remember reading these, but I didn't do them. And then I just don't have it now because I just read it instead of did it. You know what I mean? Like some classes reading is enough. This isn't one of them. Have to do it. You know what I mean? Is everybody feeling okay? Relatively better than hopefully after just the video?
Yeah, definitely.
This helped. Well, I did teach the lesson before too.
But like, so not on like the.
Okay. I much prefer to be able to interact with you guys too. Just sometimes missing school is unavoidable. But that's okay. This is going to be 2 days regardless, at least. It's budgeted to be a long time, to take some time here because this takes some doing to get good at. Has anybody figured out the situation which this method or this approach is going to be a problem? There's a situation which this could get us into a trouble. So imagine if you had something like this, and we're rotating here. So my inner radius is here. Well, let's move it up here. Inner radius is on this curve, and then my outer radius is on the same curve. That's going to be a problem. We're going to see what to do with that next time.
I'm so sorry. I'm so sorry. I promise you it was just a lecture,
okay.
so I was paying attention for the rest of the lecture.
It's okay.
I feel calm, committed, and
Oh, yeah. I was like, what?
nope,
Nope, it's mine.
And God bless. You make it exactly at the bottom of my money.
Thank you. Thank you.
So wait, no, what did you put a bag in the car so it wouldn't fall?
So actually, last year I didn't have my license, so my dad was driving, so I was just holding it. I mean, honestly,
Here's what you do. You go to your local flower shop, and they have the foam that they put the flower in the flowers, and you just like cut a piece out so your egg fits in there, and you can cut it to like fit in like a cup or whatever, because that's made to fit in a vase. There you go. It's like your own little like egg blanket.
Alright.
You're welcome.